Hello everyone, it's Benny, and welcome back to the 3D software rendering tutorial series. Since last time, I've set up a little bit of a different example scene. We have our rotating monkey head as before, now with a different texture, and we have a 3D terrain made of bricks. I promise, one of these days I'm going to get an example texture that isn't bricks, but until then, this is what I have to work with. And yeah, so as you can see, we're really starting to get a true general purpose 3D system in place now. We can do quite a bit with our software renderer. And in fact, as you may have noticed, I'm moving the camera around with inputs now. I've actually moved in a few classes from the 3D game engine. Just for example, I've got the camera class with some slight modifications. I have the quaternion class, pretty much directly taken. And I have the transform system from their 3D game engine. Modified a little bit, just taking out the transform hierarchy and stuff that we don't really need right now. And yeah, so there you go. We have general purpose transformation and stuff in place now. And that is awesome. But today, we have one more thing we want to do with our software renderer, and that is lighting. How can I take this glorious brick field we have and light it up, give it lighting effects? And that's what we're going to talk about in this video. So, the way we're going to calculate lighting is by doing a dot product between whatever direction light is coming from and the surface normal, which is whatever direction happens to be up at a particular point on the surface. So that's how we're going to be calculating lighting. And this is something called Lambertian reflectance, which I really can't do a detailed discussion in this video without getting into how shading works, how do you approximate lighting in the real world, how does light in the real world actually work mathematically, and yeah, it'll be a big prolonged discussion that's outside the scope of this video. So I'll leave a link in the description, but the point is, we're going to need this surface normal thing. So at each vertex, I'm going to have a private vector 4f m normal. And we're going to have a getter for this, so get normal. And yeah, this is just so we can calculate lighting. And this will be a new parameter here, so vector 4f normal. This won't be really too difficult to add, it's mostly monkey work here. But yeah, we're going to have to pass in the normal to all these various functions that we have that are creating vertices. M normal. And in our lerp thing, we're going to, well, we're going to need to take the normal and lerp it. So normal.lerp to hover.getNormal by the lerp amount. And there. And that's pretty much all we need to do. But how do we actually get this normal? Well, this is actually stored in our mesh. This is created in the 3D modeling process, or there's some ways you can calculate approximately what it should be, but yeah, usually it's stored in the model, so we're just going to get it from the model. When we're creating the mesh, we're adding all the vertices. I'm just going to say model.getNormal.getI. And there. So that's all we should need to do with our vertices. And this is getNorm_ols with an S. So be careful about that. Now, the way we're going to be doing our lighting is we're going to be calculating the lighting at each vertex and interpolating that across the triangle. And this technique is something called Guro Shading. And the nice thing about this is it allows us to reuse our gradients and edge system to do some of the work for lighting. So I went ahead and set those up with yet another parameter off screen because it's mostly the same thing. Not entirely, I'll be doing the different stuff on screen, but it's mostly the same. What we do is we have a new float array and gradients. We have new floats for the X and Y step. We're going to have a getter for the light amount and a getter for the X and Y step. We're going to want to initialize a new thing. We're going to want to set them to new values, which I'm going to do on screen. They're not actually going to be 0. We'll talk about this in a moment. We'll come back to this. And you're also going to want to calculate the X and Y step using the light amount array and all the other parameters. Now for edge, same stuff we did before. We're going to want new values for light amount and light amount step. We're going to want getters for the light amount. And right here in our constructor, we're going to want to create the light amount based on the gradients and the X and Y pre-steps. And we're going to want to calculate the step based on the X and Y pre-steps. And finally, in our step function, we're going to want to add our light amount step. And in render context, there's also a few things that we do every time, so I went ahead and did those off screen too. We're going to want to set up our light amount X step in our draw scanline function, and you can do this either the old way that we were doing here, or you can do it with gradients. Either way. And you're going to want to calculate our initial light amount based on the left light amount and the light amount step times pre-step. And finally, you're going to want to step the light amount by light amount X step every time through the loop. And this is all of that process that we do every single time. So now that we've finally finished adding everything we're going to add to our edge and gradient system, I have good news for you. You don't actually need to do this giant process every single time you want to add a new thing to the edge and gradient system. What you can actually do is, rather than, for instance, in edge, we have a light amount and light amount, we have some value and step for that value for everything, for every attribute. What we could do is we could have a list of all these attributes and their steps. And every time we want to add a new one, well, it's as simple as adding a new thing to the list rather than going through this big, giant code modifying process every single time. And that's kind of nice. So you can do that for the edge gradient system and whatnot if you want, and I recommend that if you want to go through a more general purpose rendering system. Personally, for this series, I know I'm just going to be using these, so I didn't bother to do that, but it's something you can do. I'll leave that as an exercise to the viewer. So now, let's actually do lighting. This is pretty much the same process we talked about earlier. We're going to want to take our vertex, we're going to get the normal, and we're going to do the dot product with some light direction. I'm just going to hard code this because I don't particularly care. So I'm going to say vector for f light dir, sure, new vector for f, and I'm going to have 0, 0, 1. So light's coming from the z-axis. So normal dot light direction. But we want to be careful because we don't want light, or we want our light in the range of 0 to 1. So I'm going to use a saturate here so that this stays in the range 0 to 1. And that's all I really want to do here, so there. And we're going to have to write the saturate function. You might want to put this in a utility class somewhere, but I'm just going to code it here because it's the only place I care to use it. So, if val is less than 0.0, we're going to return 0 because it's outside that range. If the value is greater than 1.0, we're going to return 1 because it's outside that range. Otherwise, it's in range, so we can just return the value. That's a saturate function in a nutshell. And there, that's all that we should need to do with that. Now with this, we can go to render context, and we should be able to... Well, let's not use the lighting just yet. Let's ignore the texture. Let's just create some byte for the light. And this is going to be temporary. But yeah, this is just so that we... Well, it's so we can show what our lighting looks like by itself. No textures or anything else to interfere. This is just our lighting. So, we're going to take light amount, we're going to multiply by 255.0 and add 0.5 so it rounds correctly. And that should be all we need to do. So I'm just going to say draw pixel, ij, I'm just going to pass in light for all the components. And there. So if everything goes according to plan, we should see some lighting. Or I could screw it up yet again. Well done. So, one moment. And I just put min-yvert in all the places rather than min-yvert, mid Y-vert, and max Y-vert. So now, if I build and run, you see, we get lighting. And the terrain looks okay, but the monkey, it looks almost like the light is glued to the monkey's face. And that's not quite what we're going for. So how do we fix this? What's causing this problem? So, the way we're going to solve this is by having a new matrix in our transform class. And this is going to be the normal transform. Because although we're moving our position based on how we're supposed to be transforming our mesh, we're not moving the normal. And we don't want the exact same transform we want for our position. So, we're going to have a new matrix for that. We're just going to transform the normal by that. Now, something you have to be careful of here is you have to make sure the W component of the normal vector itself is 0 for all the normals. And the reason for this is if it's not 0, then this will apply translation to the normal vector. And since the normal vector is just supposed to be a direction, not a position, that's not going to work out. So yeah, just make sure the W component of this is 0. And with that, let's go to our mesh class, because this is where we're going to need to change things. Because right now we have a transform. We don't just want a transform now. We're going to want... I'm going to have a matrix 4F for the view projection. So this is what we get from our camera. I haven't really talked about, but yeah. You'll see in a moment. And we're going to want a matrix for the transform, which is what we have right now. Now what I'm going to do is I'm going to have a matrix 4F for the MVP, which is view projection .mul transform. And as you'll see in a moment, this is exactly what I have in the main class that I'm passing in. I'm just moving this from, well, doing that in the main class to doing it here. So nothing really new here. And we're going to pass in MVP instead of transform. So yeah, nothing changed here, just really rearranged stuff. And I'm going to use the transform as our normal transform. And this is a bit of a trick. This will only work if you aren't doing any non-uniform scaling. So you aren't scaling the mesh by like 0.2 on X and 0.3 on Y or something. You can scale it up and down, just has to be by the same amount on all axes. So yeah, if you do want to have non-uniform scaling, you're going to want to take the inverse transpose of the transform matrix and use that instead. But this will work for what we're doing in this series. So now for the main, like I said, right now what I was doing is passing in the view projection times the transform. So yeah. And right now I just want that. Well, without them all. And again, the view projection is just the transform matrix I have from the camera. It takes into account the perspective projection and the way the camera, and the position of the camera and the rotation of that and such. So yeah. And there's only one more thing we need to change here, and that is, we're using the transform function in our fill triangle. So, here we're going to need normal transform too. I'll just call identity, because, well, we're not really going to want to do anything to the... And I guess I'll just type it out. We don't really want to do anything to the normal matrix here, so we're just going to pass in the identity matrix. And there. So with that, that should be all we need to do. If I build and run this, then we should see... Yeah, look at that. The light seems much more consistent now. It really seems like it's coming from this direction, and it's not just something glued onto the mesh or something. So yeah, our lighting appears to be in working order. All we really have to do now is, well, combine it with the texture. So let's go ahead and do that. So, how do we combine our light with our texture? This is actually a lot easier than you might think it is. All we're really going to have to do is modify our copy pixel method to take in light amount as a parameter. And so in bitmap, I'm going to scroll down to where copy pixel is. And we're just going to take in some float light amount here. And all we're going to have to do is multiply our components by the light amount. Seems straightforward enough, so I'm going to go ahead and put everything in parentheses. I'm going to multiply by light amount. Put that in parentheses again, because I'm a paranoid like that. And we're going to cast it to a byte. And rather than do that manually for every single one, I'm just going to copy and paste and just readjust the indices. I think that'll be a little bit easier. So +2, and that was +3. So there. So now if we build and run... Oh dear! It's not working! What's gone wrong? Well, this has to do with the fact that in Java, bytes are signed. And we really just want an unsigned multiplication here. We don't care about sign. So there's a bit of a trick you can do here. If you AND a byte component with 0xFF, it will actually treat it as an unsigned value. So yeah, it'll do an unsigned cast to an integer. So yeah, now if I build and run, yeah, look at that. We have some lighting. And it's combined with the texture, and the only thing really is that the fact that it goes completely black in some places is a little bit ugly. So something you can do to fix that is in gradients, rather than just using the saturated value directly, you can do something like, multiply by 0.9 for all of them, and then add 0.1. So this way everything has at least some amount of lighting. And this is a trick called ambient lighting. So there. And now if we build and run, yeah, things look a lot better because you can always see at least something. And there you go, we've got lighting. Now something you might notice is that the lighting on this monkey head looks a little bit flat. And that has to do with the normals in the actual mesh. The normals in this mesh actually specify to do lighting like this, so our lighting code's handling it correctly. But if you want smooth shading, you're going to have a slightly different mesh. So just to show that off, I got some different monkey meshes. Smooth monkey. They're the same mesh, just they have smooth shading. They have normals that should have smooth shading rather than what we had before. And there you go. There's the monkey head with smooth lighting. And with that, folks, I think this is pretty much a wrap. We have general purpose 3D rendering, we have perspective correct textures, we have lighting, we have transform, we have clipping, we have just about everything that the graphics card does behind your back in place. So that really covers what I wanted to cover in this series. So, let's talk for a moment. First off, if you made it this far, then seriously, congratulations. I know this has been a lot. I know it hasn't always been easy. So if you made it here, then well done. You have earned what you've got from this series. Secondly, you might be wondering, hey Benny, is this really all there is to software rendering? Is this really all you can do? And the answer is no. Not by a long shot. There are tons upon tons of techniques and things you can do that I haven't even touched on in this series. For instance, there's things like normal mapping, which lets you draw a triangle so it looks like there's more geometry than there actually is. There's things like there's more advanced lighting techniques that don't have the artifacts, the triangle-y artifacts that Guro Shading does. There's shadowing and stuff. There's all sorts of things you can do. But here's the thing. At this point, there really isn't that much difference between doing it in the software renderer versus doing it in OpenGL or something. So, that's sort of my standpoint there. Why should I cover it again, basically? Because I've already done tutorials on how to do that sort of stuff in OpenGL. That said, though, there are a few things that are software rendering specific that, well, that you probably wouldn't need in a hardware renderer that I haven't talked about. For instance, there's a whole bunch of different things you can do to improve the performance of the software renderer, and I'd be willing to talk about that if people are really interested, but my sort of standpoint there is, if you're really interested in high-performance graphics, then why are you using a software renderer? That's sort of where I stand there, and that's one of the reasons why I've chosen not to do a whole terrible bit of optimization in this series. But yeah. That said, there are still some techniques that are software rendering specific that I haven't talked about. I mean, you can do them in hardware renderer, more or less, but you probably wouldn't want to. For instance, there's one technique where you pre-calculate the lighting for the entire scene in an environment map. And what you can do is you can use environment mapping to do your lighting rather than an actual lighting algorithm like Guro Shading or something. And the advantage of that is you can get per pixel lighting that's pretty much just as high quality as it would be if you actually calculated lighting at every pixel, but it doesn't cost much more than Guro Shading. And that's, I think, a pretty cool trick. Then again, I'm crazy like that, but still. So there's things like that you might be interested in. And of course there's stuff like the edge list and whatnot, but yeah. So there is more to do. But I don't think it's terribly important to know how to do it. I'd be willing to talk about it if you're interested, but yeah, I don't think it's terribly important to cover in the series. So that's why I'm stopping here. So, thank you. I hope you enjoyed. I hope you learned. I hope you didn't mind putting up with all my ridiculous cliffhangers along the way. And yeah, so hope you enjoyed, everyone, and I'll see you next time I see you. Until then.